Welcome to this video number 7 about active high-pass filters. We'll look at the first order high-pass filter, the second order high-pass filter design block, and then look at the design of a third order active high-pass filter. But first I will take a laser pointer so that you can follow, and then we'll start. How to transform a low pass into a high pass filter. The thing is that we exchange the components. So where R1 would be in the low pass, we will have C1. Where R2 in the low pass, we will have C2. And where we had C2 in the low pass, we will have R2. And where we had C1, we will have now R1. So this is the direct transition. On the transfer function side, we are still considering cascading of second order low pass filters, but how do we transform this transfer function into a high pass? We do this by exchanging the omega to 1 over omega. And remember that omega was the normalized corner frequency. It was normalized to the corner frequency. So any frequency on this line is normalized to the corner frequency. So this is the frequency over the corner frequency. And now we suddenly have it 1 over the corner frequency. And the S is turned into 1 over S. And then the transfer function suddenly looks like this. The bandpass for the low pass gain here, the gain for the bandpass in the low pass is called A0 up here in this graph where we can see it, the low pass, is now turned into the pass band of the high pass. So we call that A infinite. And still we have these second order sections, but the filter coefficient is now AE over S, BE over S squared. Therefore, a single high pass stage would look like this, and I move a bit this one here, and a first order high pass filter where we know that for the filter tables B is equal to 0, this section is disappearing, and we still use the value A0. Actually they have the same value. We could also write A infinite here, but it's meaning the passband gain of the filter. Let's continue if it wants. Yeah. So how to make a first order high pass filter as an active filter. We can again apply the non-inverting amplifier and have a high pass, passive high pass in front of it. Here we can add gain in this section. Over here we have the inverting high pass filter of first order with an inverting gain. And we can see that if we forget C1, we just have the inverting amplifier in this section. So what are the equations for this first order high pass filter? Well, the A infinite gain is still the amplifier gain here based on R2 and R3. So this is not changed, but the second order position here removed with the 1 over S squared is now only 1 over omega RC 1 times 1 over S, and comparing that this is A infinite, and this, what we have here next to the 1 over S, is our filter table coefficient, 1 over omega RC1, R1 and C1, sorry. So based on that, we have these requirements. Then we can solve for R1 when we know C1 and the filter coefficient. So R1 can be found by this equation. And if we want to have a gain here, we have to specify A infinite, and then we can find by selecting R3, could be 1 kilo, and we can find R2. Similar for the first order inverting high pass filter. Um, the high pass is here C1 and R1. The gain is defined by R2 over R1, but we have to remember it's an inverting, so we have already 180 degrees phase shift in this. And then C1 will contribute with positive 90 degrees. So in the start, we will only have a contribution of minus 180 degrees plus 90 degrees. So this filter will start out with minus 90 degrees phase shift until this one ends, and then we're back on 180 degrees. We can see that from the sign. So the overall transfer function in the high pass, we have 1 over R is 1, and C1 is still the one that defines the high pass, likewise over here at the non-inverting. And A0 is the relationship between the feedback resistor R2 and R1. So this is given by this if we want to have gain inside it. And the filter coefficient is defined by this section here. And when we have to solve for R1, we know the value from the filter table for A1, and we have selected the capacitor. Then we can solve for R1, and we can find it by help of this equation. When we want to have a gain higher than 1 here, we can simply define what should the gain be at the pass band of the high pass filter, selecting a value for R1, and sorry, not selecting, we have calculated here, sorry, and then find the value for R2 so that it fits with the gain. Oh yeah, before I continue, in order to define a first order high pass filter, we have to specify some design parameters that the filter need to fulfill when we finish the design. And that's of course for every filter, the corner frequency and what should the band pass, the pass band gain be if infinite, and the capacity C1. And then we simply solve for R1 and R2. So, what for the second order high pass filter? Well, we use the general Salon-Key high pass filter. We can have a gain in it, or we can have a unit gain, where we only have in the pass band a gain of 1, and here we can have more gain based on R4 and R3. There is a small comment here that this type of unity gain high pass filter is normally applied in low Q filters because we have a high gain accuracy demand in the pass band. So um, when the high pass filter has passed the cutoff frequency, we have the pass band, and here the amplitude of the frequencies are not allowed to jump around. Um, when we have this gain here, the gain can actually jump around based on the R4 and R3 values of the resistor. So either due to temperature influence of the resistor, but also tolerance of filters, the resistors. When we build more filters, that these filters will actually have a tiny bit of difference in the passband due to this gain factor. And if we have a need for high gain accuracy, we would always select a unity gain silent key high pass filter. Because there is no change in these values here, or also over when I have to make many filters, produce many filters. So let's say I have to produce 100,000 of these filters, and we know that real component has tolerances, so each of these 100,000 filters can have a slight deviation in these values, and then the gain will actually, in the passband, will actually change between them. If I can't live with that, I would select high, a unity gain silent key high pass filter. The transfer function for the general silent key high pass filter, the one with the gain, we have here. So this is a huge value, and this in front of 1OS. Alpha here is the gain of the amplifier. We have it over here. But typically we try to simplify a lot in electronics, so it's very common to use unity gain amplifier. So the buffer here. So we would select alpha here to be 1, and we will also select C1 and C2 to have the same value in order to make the equation a bit simpler. So when alpha is 1 and C1 equals to C2, this equation can now be written more simplified like this. And then we know that the pass band gain for the high pass is 1. It's up after the corner frequency. The A1 coefficient we have from the table is now defining 2 over omega c r c and then r1 and c, and the value b1 is defining this section here, omega c squared r1 times r2 times c squared. And if we solve that for r1 and r2, we get these two nice equations. R1 can be found as 1 over P FC, the corner frequency, then the C value, and then the filter coefficient from the filter table. And R2 can be found again as the table coefficient A1 from the filter table, and 4 times P times FC, C times B1. So these are the options we have for the filter. So now we can look at an example, design example. And we will try in this third order high pass filter to actually apply a first order and a second order, because in order to make a third order, we actually have to cascade a first order filter and a second order filter. So we can demonstrate the filter design for both a first order and a second order by this example. First, we have to specify which of the filter actually do. So the corner frequency here, also called the -3 dB frequency, is at 1 kilohertz. We have a bandpass gain A infinite of 1. We choose a Bessel filter for this purpose to also try Bessel coefficient. And C1 and C2 and C3 equals to 100 nanofarad. We go in the Bessel filter table and look up the third order. We get a section 1 here. That is the section for the first order because we can see that the coefficient for B is actually 0. That's the characteristic for a first order, but we don't have any values for B. The interesting thing is here the KE factor that tells us the individual section here, the corner frequency for this first order filter is actually 1.323 times higher than the overall filter's corner frequency. In the second order section, this part here, we have A2 and B2. So this 2 here is replacing the E and the E here. We get these values, and we can also see that this second order section actually also is a bit higher, 1.4414 times higher than the filter's original uh, corner frequency of 1 kilohertz. And the filter's Q is 0.69 in this case. So let's get started with the design. So based on these information we have here and up here, we start using the equation for finding R1 in the first order section because we already know the capacitor C1, that's 100 nanofarad. So we place the information in the equation. So here that's the 1 kilohertz. Here we have the filter coefficient. Here we have the 100 nanofarad. And that gives us a resistor of 2.105 kilo. We go into the E-series table and look up the closest 1% value we can find, and that's 2.1 kilo. So we select that. Then the second order section, we can calculate R1 and R2 based on these equations. We fill in the information. We have FC, that was 1 kilohertz, is here. We have the capacitor, that's here, 100 nano. And then we have the filter coefficient here, 0.9996. And the value for R1 is 3.18 kilo. The closest value we can get is 3.16 kilo. So we have to accept that. Because we don't manufacture resistors ourselves to that position. So R2 can then be found from this equation, knowing we have the value here A1 and then P, C, C, B1. Putting these into the equation, we can calculate that R2 has to be 6.67 kilo. And the closest we can find in the E-series table is 6.65 kilo. So that's the standard value. The overall filter, when it's designed, is the first order designed high-pass filter and is cascaded with the second order high-pass filter. Yeah, thank you for now for watching this video 7 about active high-pass filters.